Okay, so in this video, we're going to take a look at one of the types of problems that shows up on our related rates homework. And there are a few different shapes that show up in the homework, but they are going to be handled in much the same way as this one here. So let's go ahead and take a look at how we would approach this problem. We're going to approach it using the same method that they do in the solution. And if that doesn't take too long, then we'll also take a look at an alternative way of doing the problem, um, and just to show two different solutions. But they're basically the same. So the solution that's provided by the homework website is pretty good. So we'll do it that way first. Okay, so let's read the problem here. It says a tank is shaped like an upside down square pyramid with a base of 3 meters by 3 meters and a height of 7 meters, as shown in the figure below. How fast does the height increase when the water is 3 meters deep if water is being pumped in at a rate of 0.7 cubic meters per second? Submit an exact answer. Okay, so a lot of information there. Let's go ahead and jump into our five-step procedure that we gave from our textbook. This procedure is also kind of indicated or referred to in the solution. So we want to draw a figure if applicable, that is already provided for us, and then assign uh, variables. Okay, so what variables uh, can we assign here? Well, there is this length here that goes across this square pyramid. We can call that B, the base length of the water. So the water also forms a square pyramid, and we can see that as the water is being pumped in, that base length, as this thing fills up, that base length is going to increase. So B is actually a function of time, so we can call it B of t also. What else? How about the height of the water? That is uh, going to increase with respect to time. So the height of the container is 7 meters, but the height of the water, will be anywhere from 0 meters to 7 meters as this thing increases. Okay, and we're told that water is being pumped in, and so the volume is also a function of time. The volume of water will increase since water is being pumped in. Okay, so those are our variables, V of t, B of t, and H of t. Step number 2, it says to state in terms of the variables, the information that is given and the rate to be determined. Okay, so state, well, I think in class we said state the given info. Okay, so let's see here. Let's start with water is being pumped in at a rate of 0.7 cubic meters per second. We talked about looking at the units of this. It is cubic meters per second. So that is, so 0.7 cubic meters per second. The units indicate that this is a rate of change. And cubic meters, that's a, cube, that's a volume. Okay, so dV dt is 0.7, and it is positive, right? Since water is being pumped in, the volume is increasing. How fast does the height increase? So, how fast does the height increase? That is our question. We want to find dH dt when the water is 3 meters deep. So find dH dt when h equals 3 meters. So the height at the moment in question is 3 meters. How fast is the height increasing or changing at that time? Okay, very good. Now we're also given a couple of values here. We're given the height of the entire square pyramid, and then the base length, 3 meters by 3 meters. Okay, so um, let's go ahead and move on to step number 3, which asks us to find an equation relating the variables involved in the problem. So the variables are v, h, and there is a base length as well. So the volume of this kind of shape is equal to 1/3 times, it's really 1/3 times the area of the base times the height. So we can go back to kind of, this is a little review from geometry. The area of the base here, since the base is a square, the area of this base is going to be just b of t squared. Right, that's the area of a square. And then times the height. Well, height I'm going to write as h of t because this height is changing with respect to time. So really, we could even write v as a function of time as well. V of t. In class, we left off this notation. In our homework website, they do keep the v of t. They keep that t notation. We'll see how much writing that adds to our solution. Okay, so another nice thing that they do in the solution is, well, we could move on to step number 4 and take the derivative. Take the derivative of this equation, but it turns out that there's a relationship between the base length and the height of the water. And we can see that by looking at let's go ahead and just imagine slicing this pyramid in half and taking a look at a cross section of it. Oops, and my pen jumped there for a moment. There we go. So if we slice this thing down, no, I can't really draw it, but take a slice of this down the middle, then the height of the water, let's just assume it's somewhere right here. The base length of the square pyramid created by the water we'll call b of t. That changes with respect to time. The height of the water changes also as time goes on. And the base length of the entire square pyramid we were given is 3 meters, and the height of the square pyramid is 7. Oops, I put an H there. Should be 7. Those are constants. The dimensions of the container are not going to change. And so there are actually some similar triangles here that we can use to find a relationship between B and H. So, I don't want to get into too much into the geometry, but essentially the big triangle that's formed by the container, let's see, it has these angles. So this angle that I've marked in purple is equal to this angle here. And this angle marked with 2 little marks is equal to that angle. And then both of these share this third angle. And so in geometry, we learned that if 2 triangles have equal angles, then those triangles are what are known as similar triangles. And if we divide the one side length, let's say b of t, by another side length, h of t, then if we divide the corresponding side lengths in a similar triangle, that will have the same ratio. So if we divide the base of the bigger triangle by the height of the bigger triangle, then those 2 fractions are equal. So we can solve this equation here for b of t by multiplying by h on both sides. So notice that B can be replaced by 3/7 h of t. Okay. And so this is actually a nice substitution that we can make, because if we make this substitution, v of t equals 1/3 base is 3/7 height squared times h of t. If we make this substitution, this volume function is now only dependent on the height. And so when we take the derivative, it's not going to require us to use the product rule. Here we have, b of t, a function of time, times h of t, another function of time. And if we took the derivative at this point, we would be required to use the product rule because we have a product of two functions. But by making this substitution, we're converting this entire function into just a function of h of t. Okay, so let's simplify this. So we're still on step number 3 here. This is just okay, we're gonna square. So 9/49, h of t, let's say that's squared, times h of t. So v of t is equal to 3 goes into 9 3 times, 3/49 times h of t cubed. Okay, so there is our equation that we're going to use. And so let's move on to step number 4. So that step number 3 took a little bit longer, and I think this is the step that gives a lot of students trouble, because you have to remember the similar triangles from geometry. And maybe it's been a little while since we've taken that class. Okay, but the same structure will work for the other similar problems, even if it has a different shape. Let's see here. Let me plug in my computer. Okay, so we've got the formula now for step 3. Our equation is v of t. So step number 4 is to take the derivative. So we'll apply d dt, the derivative of v of t is equal to the derivative. And you know what, I'll write the constant outside. 3/49 times the derivative. Right, the constant multiple rule allows us to do this. So we'll do the derivative of h of t cubed. Okay. So the derivative of the volume with respect to time, that's just going to be called dv dt. 3/49 is just a constant, so we'll leave it there. The derivative of h cubed is 3h squared times dh dt. Right, this is a composition of functions. And so notice that here we still have our variable h, so we're able to solve for dh dt, which is what we said earlier we wanted to find. And so now we're ready to essentially just kind of plug stuff in. Yeah, let's go ahead and do that. dv dt is 0.7 cubic meters per second, and we'll write that as a fraction. So 0.7 is 7/10 cubic meters per second. And this is equal to 3 times 3, that's 9/49. The height is, the height was, at the moment in question here, is 3 meters. So 3 meters squared times dh dt. So we want to solve for dh dt. We'll just divide. We're going to divide 9/49 times 9 square meters, right? 3 squared. Oops, square meters. Okay, and so we know that that's going to just, let's see, that's going to result in multiplication by the reciprocal, 49/9. That's a constant. And then we'll multiply by the reciprocal of 9 square meters, which is 1/9 square meters. All right, so everything cancels here. and we get dH dt equals 49 times 7, I think it's 343. The 9 times 9 times 10 is 81 times 10, 810. And then square meters cancels out two of the square meters, or square meters in the numerator, leaving us with meters per second, which are the correct units for the rate of change of the height with respect to time. And so this is our numerical answer. Notice that we got a positive number because if water is being pumped into this container, then the height of the water will be increasing. Okay, so we would say the height of the water is increasing at a rate of 343 over 810 meters per second when the height of the water is 3 meters. All right, cool. Let's see, how long did that take? Okay, it doesn't show me. Okay, so that's it. So if you want to stop the video there, you can stop it, and that is the solution. It will work very similar, in for different shapes. Um, but I did want to just quickly show, well, what if you didn't do that substitution, at least right there in the beginning? You're gonna have to do it at some point. Use the idea of similar triangles. But so let me just say a little bit about that um, to show what if you didn't make that substitution right away. So the problem's over, right? But let's go back to step 3 and take a look at this function. So v of t is equal to 1/3 b of t squared times h. So what if we had just taken the derivative here? We apply the derivative here to both sides. Then we would get dv dt is equal to, and let's consider 1/3 b of t squared to be one function, and then h of t to be the other function. So the product rule will be needed, and we would have to find the derivative d dt of 1/3 b of t squared times the second function, so f prime times g, plus g prime, the derivative of h of t, g prime times f. So can it be done this way? Yeah, it can, but it's just a little bit more complicated, right? You can see the derivative is already more complex, but we'll continue just to see, just for the fun of it. This is, the derivative is 2/3 b of t. And you can see how this b of t notation becomes a little bit cumbersome. db dt times h of t. That's why in class, for the most part, we just wrote b or h and just kept in mind that they're functions of time. So we'll drop the notation in just a moment. dh dt times 1/3 b of t squared. Okay, so let's go ahead and drop that b of t notation and just write b and h. So dv dt equals 2/3 b times db dt times h plus dh dt times 1/3 b squared. Okay, so the derivative is a little bit more complicated. And not only that, but we have, okay, so we want to find dH dt. We have h is equal to 3, but what about dB dt? Notice that we also end up with a dB dt and a b also, right? So the height is going to be, the height at the time in question is 3 meters, but what's the base length? That wasn't given. And then what is dB dt? We're trying to find dH dt, but now we need a dB dt in order to solve this. Well, the way that we can get around this is by still using this equation here. So you're still going to have to use it. I just wanted to show, um, if you try to get around it, you really kind of can't. Um, so at h equals 3, when the height is equal to 3, the base b is equal to 3 over 7 times the height, which is 3. And so then we can figure out, using this relationship of the similar triangles, we can figure out that the base length is 9/7 of a meter, or 9/7 meters. Okay. And then what about dB dt? Well, you can use this relationship here to relate dH dt to dB dt. If I take the derivative of both sides, dB dt is equal to 3/7 times dH dt. So dB dt is equal to 3/7 times dH dt. Oh, that was actually not given, right? That's what we're trying to find. Okay, so then in this case, you'll just make the substitution then of we can replace dB dt by 3/7 dH dt and then solve for dH dt. So let's go ahead and plug in. Huh? So dV dt is 2/3 B. Now the base length is now 9/7 meters times dB dt. And we said dB dt is 3/7 dH dt times h. And h was given to be 3 meters plus dH dt times 1/3 b squared, and b is 9/7 meters squared. Okay, so it's going to take a little bit of solving. We can factor out the dH dt and divide it on both sides. I'm just going to do it in the same step. So we get, let's say I'm going to factor out this. Imagine factoring it out and then dividing by what's left. And then dV dt is, this is going to become, oops, this is going to become 7/10 cubic meters per second. And divided by, let's see, can we simplify this at all? 3 and 3 cancels. And if we multiply, we get 27 on top, 54 over 49. The units on that are going to be square meters plus 1/3 of 9/7 squared is 81 over 49 square meters. So this 3 can go into this 81 27 times. Now we have a common denominator of 49. This is all equal to dH dt. And so what do we get? 7/10 divided by 54 plus 27. Let's see, that's 70, 81. 81 over 49. The units here are going to be meters squared in the denominator, cubic meters over seconds in the numerator. this is going to be equal to, if we flip and multiply, 7/10 times 49 over 81. Huh? So we get 343 over 810. And the units meter squared gives us just meters per second. Okay, so it's the same answer as before, but notice, we still had to use the similar triangles. I just kind of wanted to show, if you hadn't done that substitution at the beginning, then the derivative would have been a little bit more complicated. There would have been a little bit more substitution that needs to be done. But you still get the same answer because the relationships still hold. The relationship between B and H. All right, so definitely it would be a good idea to, if you're trying to find dH dt and you can substitute something in place of B in terms of H, as we did here, B became 3/7 H. That helped us a lot. Okay, so, all right, so we'll go ahead and end the video here and, hope that helps a little bit.